Hi, you probably learned measurements and scientific notations in class today and you were a little confused. Don't worry, I'm here to help. Or maybe you're just here to review, in which case you're in the perfect place because I'm going to give the brief summaries of everything that you need to know about measurements and scientific notations. Okay, so let's look at measurements. And when we're talking about measurements in physics, we're always referring to physical quantities, which are made up of values and units. So values are the numbers. When you say 20 centimeters, 20 is the value, and therefore centimeters is the unit. And when we dive deeper into the units, there are these things called SI units, which are standard units that are used worldwide. Any number related to science is almost guaranteed to be written in SI units. So it's really important to know what SI units are. SI units are comprised of fundamental units and derived units. And derived units are basically just a combination of fundamental units. So a common one you would see is the unit for speed is meters per second. And you can see that that's just a combination of meters and seconds, which is the unit for distance and time. So one thing to note is that there are 7 exact fundamental units that is used all over the world. But in IB, you only cover 6 and you don't really look at luminous intensity as much. So don't worry about it. It's handy to know that it exists and that there are 7 fundamental units, but in IB, you only cover 6. So the 7 fundamental units are mass, distance, time, electric current, amount of substance, and temperature, and they're all denoted by kilogram, meter, not kilometers, meters, seconds, ampere, mole, and Kelvin, not Celsius or Fahrenheit. The last thing I want you to know is that in your data booklet, you'll have this, which is a table with a bunch of values that may seem a little unfamiliar. But if you look at it, basically it's handy when it comes to converting units. So when you're, say, going from kilograms to just grams, you would multiply your kilogram value by 10 to the power of 3 to get grams. And the same works for all the values in this table. So this comes in really handy. It's in your data booklet. Make sure you refer back to it. If you're going to take an exam, this comes in really, really handy. So let's talk about scientific notations. This is obviously not only in physics, but it's in every branch of science that you encounter. And it's basically a way of writing a certain number, or a way of writing numbers in a more consistent and manageable way that are easier to look at and easier to compare. So the gist of it is that A, the value A that you see, is just a number between 1 and 10. They can be decimals, they're usually decimals. And B is an integer, which is basically just whole numbers that we use commonly, 1, 2, 3, 4. They can be negative integers as well. So let's look at examples here. 1, 2, 3, 4, 0, 0, 0, 0, with 4 zeros at the end. If you read this, it would be 12,340,000 in the value. And we can rewrite that in scientific notation by writing 1.234 times 10 to the power of 7. And if you expand this, mathematically, it makes sense. Of course, it makes sense. And the upside for writing and the advantage to writing numbers in scientific notations, as I said before, is to make it really easy for comparisons. So if we look at this absurdly small number here, we can rewrite that in a very similar form, and all of a sudden we can compare these and say, oh, this is much smaller and this is much bigger, and we can kind of visualize how far apart they are. These scientific notations also come in really handy when you're using those metric multipliers that I mentioned before, and it makes math so much easier when you're dealing with conversions of units. So scientific notations come in really handy when you're rewriting things in the appropriate amount of significant figures. So what exactly are significant figures? Well, significant figures are also another way of scientists coming together to come up with a more consistent way of displaying and interpreting values. So I want you to just know that all figures are significant except for leading zeros and trailing zeros. And there's an exception to trailing zeros. It's every trailing zero that's behind the decimal is technically a significant figure. So if we look at the example here, 0.0001234 has 4 significant figures because 1, 2, 3, and 4 are significant, but 0.000 are not, and that's because they're leading zeros. Trailing zeros, in the same way, these 4 zeros are insignificant. They're not significant figures. And these 4 numbers in the front, 1, 2, 3, 4, are going to be considered significant figures. So here's some examples. 1,234,000 it has 4 significant figures, right? Because these trailing zeros don't count as significant figures. And if we look at this example, 59.40, this one has 4 significant figures because the 0 is behind the decimal. So that's what I meant when this applies only when it's in front of the decimals. And lastly, we have 30.4, which has 3 significant figures, 1, 2, and 3. All the figures in this number is significant. So it's really important when you're writing a lab or you're doing calculations that you keep your significant figures very consistent. And that's because when it gets to really big numbers, it gets very inconsistent. And 50.3 kilometers is different from 50.345 kilometers, because when you convert that to meters, at first, when you're looking at it from kilometers, you feel like there's no big difference. But when you convert that to meters, that's a whopping 45 meters of a difference. And that's really significant when it comes to measuring things perfectly. So just remember, if that didn't really make sense to you, significant figures must be consistent in anything that you do. If you're calculating and you have a value with 2 significant figures and 4 significant figures, you have to have a consistent number of significant figures. Lastly, I want to cover operations, and more specifically what to do when the number of significant figures is inconsistent throughout your calculations. So, for example, if multiplied or divided, you round the final result to the lowest significant figure. So say you divide 131 by 29, and you'll get a very precise number of 4.51724. And theoretically, that would make sense. But if you're doing real-life measurements, that is not really trustworthy. You can only really trust until the lowest significant figure, which is 4.5. So because 29 has 2 significant figures, you have to write your final result in 2 significant figures. And if you round that, it would be 4.5. Same thing, or differently, I guess. If the numbers are added or subtracted, you have to round to the lowest decimal place. Not significant figures, but decimal place. And so if you have 125.29 plus 12.6 is equal to 147.89. You have to round that to 147.9 because the lowest decimal place is the 10th, and you have to round it to that to be more accurate and precise. So that's basically what measurements and scientific notations and significant figures are about. Whatever you do, whenever you're dealing with numbers, make sure that every number has the same amount of significant figures. For example, if you have data entries in your lab, make sure that all your data values are of a consistent significant value. So if one of your numbers have 2 significant values and one of your other numbers have 3 significant values, that doesn't make sense, and you'll get points cut off for that. So watch out for that. And when you're solving exam questions, unless told otherwise, make sure you use the number of significant figures used in the values within the question themselves. So hopefully that helped. If you have any other topics that you want me to cover in physics, math, and chemistry, you can leave it in the comments below. I am a student myself, so I apologize if some of the explanations were a little off, but I will try my best for future videos to be as clear and precise as possible. Thanks for watching, guys.